So I'm going to tell you about an open source project called Ray for doing parallel and distributed programming in Python. And this is a project I've been working on for a little bit with a bunch of people at Berkeley. OK, so you probably haven't heard of Ray before. So to orient ourselves, Ray is similar to some of these other projects that you may have heard of. So if you're familiar with Spark, Dask, Celery, IPython Parallel, these are all several of many different tools you can use to program clusters. And actually, IPython Parallel is the first tool that I used when I was an undergrad in college to start trying to program stuff and run different functions on large clusters. And that was really powerful to see. Similarly, Ray is compatible with tools like TensorFlow, Kubernetes, your Python library of choice. So really, we're trying to play nicely with the whole ecosystem and have a, that's one of the great things about Python is that it has so many great libraries, right? And so being able to leverage all those in the distributed setting is something that we're trying to do. OK, so what's the problem? Well, we know that Python's taking over the world. Many people are learning to program in Python. More and more people are learning Python on their laptops. But at the same time, everything's moving to the cloud, right? So distributed computing is becoming the default mode of computation. And the thing about distributed computing is that it's really, really hard. So a lot of the time, if you want to build some application that runs at scale on a cluster, not only do you have to build your application and the logic for what your application is doing, you often also have to build a lot of the infrastructure to run your application. So you might have to think about things like what happens if a machine fails, or how do I divide up the work between the different machines and schedule the tasks, or how do I transfer objects efficiently between machines. There are a lot of lower level considerations that you start to have to think about when you're running programs at scale. And as an example of one kind of application that I'm talking about, imagine you're running an online service where you're recommending products to users, and you have data, things that users are doing or searching for, all that kind of data streaming in. You're sort of processing that in a streaming fashion. You're incrementally training new machine learning recommendation models. And then you're taking those recommendation models and serving recommendations back to users in this closed loop. So this is an example of if you're running this kind of service, each of these components needs to run at scale. And it's just one application. But to build this, you often, we see companies doing this by combining many different distributed systems together. So to do the data ingestion, they might use tools like Apache Spark or Flink for stream processing. Then for the training part, they're using distributed TensorFlow or PyTorch. And then for serving, they might have some in-house distributed serving system that they built. And then they have a lot of glue code to combine all these things together. So it's very difficult. So to put that in another picture, why Ray? Here's what it looks like today. Your code in the middle, that white box in the middle, that's the part that really you should be thinking about, the application logic that you want to write. But it's only a small part of the picture. Often you have all this surrounding stuff to configure things and set things up and make sure things are running smoothly and monitoring all of that. We're trying to move over to this picture where this blue box, we provide this fairly simple API that consists of tasks and actors. So that's our way of taking Python functions and Python classes and translating those into the distributed setting. And you can write your code using that API. You can get it working on your laptop. And then you can take the same code and run it anywhere. So that could be on Kubernetes or AWS, GCP, or a large multi-core machine. OK, so I want to say that we have, it's pretty early on for this project, but we have a growing number of use cases at different companies, and production use cases, research use cases at startups, bigger companies, universities. It's an open source project on GitHub, and we're seeing a growing amount of activity, contributors, contributions from companies, and things like that. I'll say more about this at the end, but we are trying to really get more people involved in this project. OK, so now I'm going to say a little bit about the API, and I'll give a quick demo of how you can actually use it. So one thing that we're doing is we're not really introducing a lot of new concepts. So if you think of something like Apache Spark, it introduces this concept of a distributed data set. Or if you think of something like TensorFlow, it introduces this concept of a neural network. And then when you write programs using those frameworks, you architect your program around those concepts that they introduce. We are trying to take the existing concepts of Python functions and classes and directly provide a way to translate those and run them in this distributed setting. So here are two Python functions. One just reads a file and reads an array from that file, and the other adds two arrays together. If you're familiar with futures, what we're doing here is we can just add this ray.remote decorator. And now when you invoke one of these functions, it immediately returns a future, or this object ID, which refers to the eventual output of the computation. And it starts this, it submits the function as a task to run asynchronously in the cluster somewhere in the background. And so because it returns immediately, you can submit a second copy of the task. And those two will run in parallel because the first one hasn't finished yet. And of course, you can submit a third task that depends on the first two. And if you want to actually retrieve the outputs of the computation, you can call ray.get to retrieve the actual outputs. And so if you're familiar with the concept of futures, that's exactly what's going on here. It's a very powerful concept, and other frameworks do this as well, other programming languages as well. And this lets you can build a lot of powerful applications this way. One thing you can't do with futures, though, and stateless and pure functions is encapsulate mutable state in objects, right? So when we program in Python, it's very normal to use classes in addition to functions as a way to encapsulate mutable state. And in machine learning, that comes up all the time. So the way we do this with our API, and I'll show this quickly, is you can take a Python class, an arbitrary Python class. You can decorate it with this ray.remote decorator. And now you can just instantiate it with this when you create an instance of this class, that starts up a service somewhere in your cluster, and you can invoke methods on it. You can start multiple copies. They can talk to each other. And you can use these as building blocks to build some fairly sophisticated stuff. So I'll give a quick example of what that looks like, hopefully in IPython. So hopefully this is visible. So ray is a Python library. I'm importing it. And then I'll call ray.init. So this is starting several processes. This is starting a scheduler, an object store to hold outputs from tasks and things like that. I'm also going to import a couple libraries. And so I'm going to define this parameter server class. So if you're coming from a machine learning background, a parameter server, or not from a machine learning background, the parameter server is basically a key value store. It's used for distributed training in machine learning a lot of the time. Basically, it holds the weights or the parameters of a machine learning model. And then different workers that are sort of computing updates to those models talk to the parameter server to get the weights, and then talk to the parameter server to update the weights. So this is you can think of it as like a key value store. You just stick stuff in it and then retrieve the stuff. So we're going to initialize it by saying that the parameters are just a vector of zeros. And then it has two methods. One for getting the parameters, which will just return self.params. And then one method for updating the parameters. And this is going to take in some gradient update, and we're just going to add or subtract that from the parameters, right? So as a Python class, it's very simple, just two methods for getting and updating stuff. OK, so now with Ray, we're going to add this ray.remote decorator. And now when I instantiate it, I'm going to call parameter server.remote. So this is starting up a new process somewhere in my cluster. This is actually on my laptop, but if I were working on a cluster, it would be in the cluster. I could start up multiple copies, and there would be multiple of these services. And now I can sort of invoke methods that run remotely on this service. I can call ps.getparams.remote, and that returns a future like before, and fires off this task that runs on the actor process. I can get the parameters, right? And this is so it's just a vector of zeros right now. I can update the parameters and pass in, say, a vector of ones. So then if I go back and get the parameters again, the parameters have changed. So that's just starting up one service, and now I'm talking to it. But say we want to actually do some machine learning training, right? So I'm going to define a worker function and pass in a handle to this parameter server. So this worker function is going to be able to talk to the parameter server. And what it's going to do is it's just going to loop around for a little bit. And in each iteration of the loop, it's going to get the latest parameters from the parameter server. So I'm going to call ps.getparams.remote, and then call ray.get on that. Then I'm going to compute some sort of gradient update. And here I'm just going to make up a number. But this is where you would use TensorFlow to compute the actual gradient. And you'd use some data that you have. Then we're going to sleep so we can just watch it happening in real time. And then we're going to take our gradient update and ship it back to the parameter server. So I'm just going to pass that into the update params and send that off. And then that'll loop around. So now I'll start a worker process. So I'll call worker.remote, pass in the parameter server. I can start 3 of them. And now if I go back and get the parameters from the parameter server, you can see they're sort of updating in the background. So what we did is we started this parameter server object, which has this interface. And then we started 3 of these worker processes, which are talking to the parameter server to call its methods and get the results and return them and things like that. And it's just a few lines of code. If you wanted to, if the parameter server became the bottleneck, you could start at multiple copies to sort of shard things. If the workers became a bottleneck, you could start more copies of that. It's very configurable. This is the kind of thing that is typically implemented as a standalone, like big C++ data code base. And here we're implementing it in a toy example in a few lines of Python. So that's what I wanted to show you about the API. OK, now I'm going to go back here and conclude. Oops. OK. Right, so I want to say a bit about other systems. So I mentioned Dask, PySpark, IPython Parallel, Celery. I think the things that really we think about that differentiate Ray are stateful computation. So actors and actor fault tolerance, being able to, actually in this way, Ray is more like Erlang than it is like these other systems. But we find that for a lot of machine learning applications, we really need the ability to encapsulate mutable state, whether that's the state of weights of a neural network or the state of some simulator if you're doing reinforcement learning. The other thing we are really focusing on is performance. So if you're building some high throughput serving system or a streaming system that's handling millions of queries or responses per second, you can't really have a centralized scheduler to do that. So you need a distributed scheduling architecture. For machine learning applications that we care about, there's a lot of large numerical data, so we care a lot about using shared memory and zero-copy serialization. We use the Apache Arrow project to support that. The core system is actually built in C++, and we have language bindings. We primarily support Python, but we also have support for Java as well. And that's really cool because a lot of companies have their core business logic or in Java. And so maybe they're like streaming logic in Java, but then their machine learning is in Python. And so you can enable these like streaming systems to also make use of the machine learning and in the same application. So that's another tidbit about Ray. And just to conclude, we're trying to make it easy to program at any scale. So to let people start, prototyping on their laptop, get something working, and then not even thinking about scale, and then go in after the fact and spend half an hour and scale it up. And so I talked about this core system, this blue box on the bottom, but it's only useful if we have an ecosystem of libraries and tools built on top. So we've been building libraries for reinforcement learning, hyperparameter tuning, and experiment tracking. We have more in the pipeline for serving and data processing and things like that. And so we imagine the scope of this project to be pretty big, and we want to build a lot of stuff on top of it. So this is my contact info. If you're interested in working with us on this project, that's something we'd be super excited about. We actually started a company recently to try to invest more in this project and put more work into it. And so if you're interested in working with us, please let me know. I'm going to put my contact info on the Meetup page, and it's also online. So please feel free to reach out. Thanks a lot.